I'm Dr. Simon Thorne. I've been a lecturer in computer science for nearly 20 years next year. When I joined my university, I kind of wondered what the future would hold. For me, it was an exciting time to be part of, research and education that would drive computer science forward. What I imagined was a kind of utopia where we would be churning out brilliant programmers, master software engineers, that catastrophic software failure would be a thing of the past. Humans and computers would work in total synchronicity, a kind of utopia. And we would use AI where we absolutely had to use it. The reality is quite different, unfortunately. So I'm 20 years down the line, and I talk to my students, and they all hate programming, all of them. I can see a few nods there. And I've had students turn down exciting jobs in AI on the basis that they would have to learn to code. It's a curious thing to me that they aren't, it isn't part of their second nature. And if we look at, say, software error rates, nothing really has changed in the last 40 to 50 years. We still see 2.5% errors per line of code, even after we have tested and debugged it. So testing and debugging is where we pass data through it, we maybe notice some problems, and then we go back to the software and we try to fix it. In non-debug software, we see that error rate at about 5%. Now, if we look at non-professional software development, which we sometimes call end-user computing, citizen computing, or shadow IT, the picture is much worse. The vast majority of this kind of activity is done in spreadsheets. And I'm the chair of the European Spreadsheets Risks Interest Group, and we've been studying this for the last 20 or so years. And the quality issues that exist in spreadsheets are really significant. So 88% of all spreadsheets contain material errors. And the best approaches to fixing those problems only captures about 60% of the mistakes. And we know from the profile of the people doing this kind of work that they don't plan, test, document, or anything that a normal software engineer might do. And we still have catastrophic failure as well in software. It's still happening. These are 3 recent examples. So the Horizon Post Office scandal is an interesting one in that there are now 700 postmasters convicted of false accounting and similar offences in jail based on discrepancies that arose from the accounting system, which is Horizon, and their cash draws. So there's a discrepancy. It turns out, of course, that it is not that. It is the fact that the software is incredibly poor quality, and the vendors knew this before they shipped the software. Senior developers have said that there were thousands of bugs every time they ran it through their test environment. Other developers have used very colourful language to describe the quality of the software, which I can't really repeat. And the investigators were guilty of confirmation bias. So the investigators believed that the postmasters were up to no good. And so when they saw these discrepancies, they immediately attributed it to the postmasters and not questioned the quality of the software. At the moment, 88 of those convictions have been overturned, with many more expected. In 2020, we had the news that the UK test and trace system, which was the beating heart of the UK's response to COVID, had lost 16,000 positive test cases. How did this happen? Well, it transpires that in the pipeline of data, when you're bringing data in from all sorts of different places, there was an old version of Excel used at some point, a .xls format. Now, the .xls format can only deal with 64,000 rows of data. And so what happened is that it encountered a file larger than that. And in those circumstances, it just cuts the bottom off. So the rows that it can't represent just get lost. So that's how that's how those people wandered around not knowing they had a positive result and infected other people, and no doubt people died as a result. the Airbus MCAS system, which is on their 737 MAX aircraft. This piece of software was written to automatically take control of the aeroplane in certain circumstances. So the design of the MAX was a sort of leap forward for Airbus in terms of fuel efficiency and range. And they did this by putting bigger engines on the aircraft, basically. However, the wings were so low on the aircraft that they couldn't put them directly under the wing. They had to mount them slightly up the wing. And what this meant was that on occasion, the aircraft's nose would kind of pitch up. So MCAS was written to detect that and control the aileron and push the nose back down. Now, in both accidents, what happened was that the MCAS relies on the angle of attack sensor, which is a movable sensor which basically just shows which way the aircraft is pointing. Now, one of these was mechanically jammed, and another one was giving an inaccurate reading. And so when the system reads that value, it thinks that the aircraft's nose is pointing up, so it starts to correct that. Of course, in reality, the aircraft was flying straight. And so what happened is the aircraft just nosedived into the ground. In all cases, if we, in UK Test and Trace and the Airbus examples, if they had tested these systems properly, there's no way that these things would have happened. And these people wouldn't have died in the aircraft, and those 16,000 people wouldn't have gone around infecting more people. I think probably the Horizon is probably the worst example, because they knew it was bad quality. And they did it anyway. And it kind of typifies a carelessness and a disregard for people. So why do we find programming difficult? Why do we commit mistakes? And how do we make bad decisions? And the answer is human factors. Human factors is kind of the suite of things that drive human error. And then software error is really just human error in software, which is human factors. It comes down to being fuzzy by nature. That's what human beings are. We're very good at making quick snap judgments. This has served us well in terms of survival, because we can identify and avoid danger very quickly. But what that costs us is precision. So precision requires us to study, to concentrate, to reflect and repeat. And we find that difficult. And I think that's why my students don't like programming, why people tend to not like things like mathematics, because it requires that level of concentration. Now, this is Donald Mickey. He worked with Alan Turing at Bletchley Park, and he was interested in human-computer interaction issues. He did a lot of work based on human versus computer chess matches. And the conclusions that he came to were that the machine was very, very good at manipulating logic and mathematics to plan out all of the possibilities of moves on the board. But humans really struggled with that. And it meant that the machine was better, and the machine could beat pretty much any human player. He also noted that whilst the machine could do that reliably, it was very narrow in its intelligence. So it could only do that. It couldn't appreciate anything else, couldn't contextualize the world or anything. So to that end, he came to the conclusion that our current mode of sort of human-computer interaction is limited by that. So we give ourselves the difficult job of doing the programming, i.e. manipulating mathematics and logic, whereas what we should really be doing is giving that to the machine. And in a sense, this is kind of what AI is. And to some degree, that has come true. But I think the way in which it is panning out now is going to provide us with lots of issues in the future. So we have these things called low-code and no-code tools. And what this allows anyone to do is to create software code from different approaches. One approach is to use plain English. So you can write a sentence in plain English, and it will transform that into code of your choice. And we can go all the way with this. We can write a complete piece of software using that approach. The problem with this is that it provides accessibility to software engineering to non-software engineers. And we only need to look at the problems in spreadsheets to know what that kind of accessibility brings. So we're going to see a programming hell, not a utopia, that will contain, millions of untested, unplanned applications with no documentation, whose authors can't even explain what the software does or how it works. So what can we do about this? There's no changing it. There's no stopping it. Something like this is happening, and it's happening for a reason. It's the same kind of thing with spreadsheets, because we've been studying this for 20 years. Quality is always something that comes up. And so the question is, why do we still use them? Because we want to. And they're useful and popular and easy. And, so there's no kind of stopping this. How do we deal with it? I think we have to ask ourselves some basic questions. Like number one, am I going to be putting anyone's life in danger by writing this software potentially? What are we actually risking when we use this? And have we considered how human factors might impact the use and development of this software? The truth, I suppose, about AI in general is that it's the Wild West. I do a lot of work in this sphere, and we have new terms like data science, but I'm afraid there is no science in data science. It's completely ad hoc. So there's no standards in validity or in the impact of decisions made, and we see that occasionally in our lives. And I think, as an analogy, it's like building a bridge, but not bothering to plan what you're going to make it out of, or calculating how much weight it should be able to take, and just hoping for the best. So what we need around AI are standards. So I think that we have to acknowledge and incorporate AI artifacts and automation artifacts into software engineering in a formal way, so that we can be sure that they work. And then we can use AI in the way it should be used, and we can build verification and validation models based on test data. So we can take test data, we can generate a model from the test data, and then we can use that to validate what the software is saying. We might make mistakes in the software, but we are unlikely to make mistakes in the test cases. And so that will give us a truer picture of reality than the software. Also, I think we need, it's time for some real accountability for people for avoidable failure. The Horizon scandal, for instance. We need some kind of proactive legislation that prevents vendors like that from releasing software that is full of problems and has ended up, with 700 convictions. Following the collapse of Enron, which was a big accounting firm in the United States, they introduced something called Sarbanes-Oxley. And Sarbanes-Oxley made the chief information officer personally criminally liable for any inaccuracies in accounting reporting. And I feel like we need something like that to make individuals personally responsible. And I believe that that would stop, these kinds of things happening. I think as software engineers, we need to stop taking the easy route. We need to stop looking for, shortcuts. We need to stop abandoning our established wisdom. And I think it's time to sort of recognize programming as an art and not a commodity. I think programming is an inconvenience that we like to throw money at, that we want done quickly, but I think that leads to many of our problems. I think we have to take more time and consider it more. And we have to recognize and test for human factor issues in software engineering processes. That is an underrepresented area at the moment. So let's hope then the next 20 years is much better than the last. Thank you very much.